Recommendation systems at eBay. Aren't you excited? So eBay, one of the largest semi-unstructured marketplace, and I'm going to talk about why it's a semi-unstructured. So as I said myself, I work for eBay, manage an applied research team, or at least I did, just moved the position to start a new role. This talk is going to be when I was in the merchandising team. That's the team that works on recommendation systems at eBay here in New York. So the agenda for the talk, we're going to start with a brief overview of eBay. We're going to go into deep dive on the complementary algorithm. Then the complementary algorithms, those nasty recommendations you get once you buy something. So you know we always harass you with more recommendation things that you should buy. That's a complementary algorithm, and I'm very much proud of it. And then we're going to talk about some usage of word-to-vec. I don't know if some of you have heard the concept word-to-vec or got to work with it. It's pretty awesome. So we did some content-based recommendations with word-to-vec. And we're going to finish with maybe a minute talking about the future, depending how much time I have. OK, so we're going to start, as I said, with an introduction to eBay, eBay NYC, and what are the recommendation systems that we have at eBay, the challenges and the solutions. So eBay, I don't know if you know, but everyone, when they think of eBay, they think more of a C2C. C is consumer to consumer, B is business to business. So everyone, when they think of eBay, especially, I know I heard just recently Obama saying that he's going to sell his parking ticket for the White House at eBay. So everyone thinks about like people like you and me all selling to other people like you and me. Well, eBay is not really just about that. Actually, a lot is more of a B2B. So when businesses sell to other businesses, like Best Buy would sell there to maybe some retailer has a small shop. So you'll buy from Best Buy in eBay or on eBay, which from a data science perspective can be a challenge because we really are trying to optimize the site for people like you and me. So if we're trying for learning based on businesses, that might be a challenge. So what is our data? We really love data. What does data mean for eBay? So we have users, a lot of them. Some of them are sellers, some of them are buyers, some of them are both. I wish, as a data science, I would have known for every given time if someone is searching for something because he wants to sell it, because he wants to buy it. And it's a different. We have a lot of items, a lot, or millions, a lot, billion. Those items have titles, so those things you see that describe the item. It's 80 characters long. They have properties, like the brand is Apple. The size is 16 gigabytes. We have the category. This is a cell phone. We have the image. More often than not, someone is not putting a really good image, just like taking a snapshot, and that's the image. Sometimes it's dirty, sometimes it's clean. You have the description. More often than not, people are using the description to advertise their entire store. So data science, again, it's very hard to just use it. And of course, behind the scene, as I said, when I was working in structured data, the entire team in Israel and some of it in San Jose, the headquarters, are working on creating structured data. And that's products. So we have a catalog, and sometimes the items are attached to products. We really like when that happens. Sometimes the seller does it. Sometimes we, as a data science, do it behind the scenes. And we have some metadata, same properties that the seller can put to describe the item, we also try to extract from name entity recognition, basically. OK, so eBay NYC. eBay NYC is an office not far from here in 6th Avenue, working on the homepage of eBay, the recommendation systems on the site, and third-party ads, and more. We have two main teams or main profiles of teams. Front end, this is a full stack engineering, design, architecture, security, all the heavy core of building a site-facing services. On the other hand, we have the back-end teams where I'm coming from, which is more an applied research team. The applied research team is not just scientists who build the algorithm, we use a dupe and everything. We're also the one responsible for the engineering of it. So the people that we're trying to hire are a mix of both. The way we see data scientists, we see it as a magical place where that person is both a mathematician and an engineer. And of course, we run all the A/B tests, we analyze it. We have an analytics team, a great analytics team that helps us, but we work together. So semi-structured marketplace or semi-unstructured marketplace. So if we talk about it, if we put an X between unstructured and structured, the way I like to explain is using examples. On the structured side, we'll find Amazon. So I don't know if you got to sell things on Amazon. I'm pretty sure you all got to buy stuff. But if you sell, you really have to provide a UPC, like a unique identifier. So everything there is cataloged. The history is complete. They know everything, which is great. On the other hand, there's a place like Craigslist to represent the unstructured, where you just come and you put a title, an image, similar to eBay, but it doesn't look like they're trying to create structure. It's more in the sense of a flea market, where Amazon represents Best Buy. eBay is somewhere in the middle, more closer probably to Craigslist, in the sense that if it's on your mind, it's on eBay. So we have a very big inventory, very unique and broad inventory. But not all of it is structured. So if some manufacturer in China creates a T-shirt and he wants to sell it on eBay, he can. And we don't know anything about it. Sometimes the title just have some hearts in it, and we really don't know anything. Yeah, well, we consider it a challenge. OK, so what is our recommendation system? So I created this as a flow where you can see the user. There's like a thing called a shopping funnel. So even in commerce, in real commerce, everyone has that shopping funnel in mind. The awareness is more like the window you see of the store, more like the commercial. At eBay, we try to solve it using collections. It's very similar to the Pinterest board, and you see that on the homepage. In a sense, the homepage is our window to the store. So maybe someone will see there a camera, a guide, or a story, or a board about a camera or a collection. On the other hand, once you know you want cameras because you saw it in the window because a friend told you because you just need one, then we go through the interest and desire phase. There we have a bunch of algorithms under the track of discovery, where we're trying to tackle broad queries, where we're trying to help the user understand, do you want a DSLR or do you want a point and shoot? If you know you want a DSLR and you're looking for Nikon, maybe you want Canon, because people who bought Nikon also like Canon, you know those things. So you will see it usually on the right strip on the search results page and on the view item on the bottom. Afterwards, and this is something less similar to the real commerce, this is something really that exists on a site like eBay. Once you know exactly you want that Nikon point or DSLR camera, now it's about finding the right deal. So this is where the similar algorithms comes into play, and there we're trying to find the relevant deal for you. And of course, there's a lot of compromise you can make. It's not something, there's not one deal for everyone. You might be willing to compromise on the condition. You might be willing to compromise on the amount of time it takes to ship. All of those things afterwards transfer to money. And what are the things that you're willing to compromise to get a better deal? And last, and that's where we're going to focus on this talk, it's the complementary. Once you made that purchase, if we're talking about the camera, now you already bought that Nikon DSLR. Now we want to match it with a case. We want to make sure you're still engaged with eBay on the one hand, and we want to help you. The way I see it, we just want to help you. So the complementary. Complementary, if you look at the literature, is an item-to-item recommendation problem, or recommendation system, where you have an item and you want to find another item. So sometimes you have the user, but it doesn't really matter. Even some people can check out, can make a purchase as guest. Even then, we want to recommend them those things. So it's more of an item-to-item. Of course, we use users, but you're about to see how we do it. So what are we trying to do? We're trying to usher buyers from one shopping mission to the next. So everyone knows everyone when talks about recommendation problems, because of the Netflix challenge, everyone knows Netflix, and it's great. They've done so much for the field. So basically, if someone watched or bought Game of Thrones Season 1, we probably want to recommend, you don't like it? We probably want to recommend Season 2, Season 3. But also, we want to see the taste, and we want to see, OK, so Lord of the Rings is a good recommendation. The Hobbit is a good recommendation. On the other hand, eBay has more than just movies. So we have the Netflix challenge, but we really have so much more. Another example is in electronics. And this is where we want to inspire. We want to use this placement. We want to use this place to inspire people to other inventory that exists. So if you buy a phone, we want to recommend you buy a case, batteries, a glitter case. And of course, as I said, a lot of buyers at eBay are really B, in a sense that they're either businesses, they're resellers, or they're collectors. So if someone buys a baseball card, what we really want to do is recommend more baseball cards for him, because that's what he's interested in. But hopefully they're from the same team and they're not the exact same item. So why is it difficult at eBay? Why is it difficult at eBay? So we're going to explain in a bit about what are we talking about, what is the methods. What's going on here? Sorry, there's a problem with the slides. I'll fix it in a second. OK, so collaborative filtering. The way we usually solve recommendation problems in the literature is with collaborative filtering. So when I just joined eBay, I got a lot of, why can't you be like Amazon? They do a really good job with recommendations. It's true, they do a really good job. But let me explain why. So the entire field, the entire concept of collaborative filtering, which is the system, the method under machine learning to solve recommendation problems, is let's start with a matrix of a users in one hand and the products in another hand, or items in another hand. And then we're going to start and put in the reviews. That person liked it, that person didn't, that person might like it. Once we have that, now we're going to try to find the missing. We're trying to fill the missing gaps, right? The missing holes. So maybe that person, we want to know if he likes it or dislikes the product. So what we do is we find close users, we find similar users, and then if they like it, then he's going to like it too. If they don't like it, then he's not going to like it too. That's basically the idea. But of course, as everything, it's start with an idea, simple idea, but a bit more complicated. So we have a user-to-item recommendations, and the idea of if we create this matrix, then as I explained, if you want to learn what's the recommendation for an item, you learn from other similar users. We're talking about item to item, right? So in the same matrix, don't look at the rows, look at the columns. If you look at the columns, then those are really vectors, and then you can compute a cosine similarity between a vector. If it was a full vector, because those question marks somewhat of a problem for computing cosine. However, usually what we do is we fill those missing values with zeros, and then we compute cosine similarity. And if you think about it, what is a cosine? It's really the intersection divided by the union. So the people who bought this and also bought this divided by the people who bought this or bought this. And of course, it doesn't really end there because those matrices are very, very sparse and very, very huge. So some techniques like ALS, which is a matrix factorization, try to compress into a more dense matrix. And we do all of them. So why is that difficult in eBay? I don't know if you can see. Oh, yeah, you can see. The reason it's difficult at eBay, it's because first, on the user-based recommendation, the collaborative filtering, the entire concept of frequently bought together, it's somewhat of a problem because when I list an item, item's volatile. When I list an item, it's there for at most a week, and there's one of it. If I don't have a product, if I don't know what it is, then how can I do a cosine similarity? The entire vector will be all zeros, and at best have one somewhere for some user. The cosine will always be zero. So that's not really an option. The entire concept of implicit feedback. When you go to Amazon, you give a feedback on what you got, and you can do it because it's all productized. At eBay, it's more a challenge because we support a lot more inventory, then we come to a situation where users are not giving us feedback. And a content-based, and of course, resellers and collectors skewing the model. There's another option, which is content-based. So the idea, if you watched a horror movie, you might want to watch another horror movie. But even that, we don't always know. It's very ambiguous. It's very partial at eBay. So luckily, we already have it in production. We have something that's working. You can see it on a mobile. You can see it on emails. You can see it in different channels. So what do? We try to look for static entities. For static entities like properties, like categories, like products, then we can do this. So if you look at the same matrix we presented before, now we have a model for categories. So there is 18,000, if I remember correctly, 18,000 categories in the US. It's a small number. So if you create a matrix users and categories, then you can look at two vectors, and you fill one where user bought the item and zero when user didn't. Sorry. And then you can look at the cosine similarity between, for example, phone and cases. Now you can understand it's about finding the nearest neighbors, right? If I can compute for every vector the cosine similarity for each and every other vector, and the vectors are representing the categories, then it's about finding the similar neighbors, the closest neighbors to me. And those are the recommended categories. So for this example, for cell phones, we really got the matching category. The closest category is cases. It's perfect. It doesn't really end there because this is a problem of compatibility. You don't want to recommend an iPhone case if someone just bought a Samsung phone. And it's a matter of personalization. Probably that person will not like the glitter phone that's recommended over there, although it fits his phone, recommended case, although it fits his phone. Sometimes when the category is granular enough, small enough, that's all you need. So for the baseball gloves and mitts, they recommend the baseball bat and gloves. That's a perfect, right? Because it's not about finding the right item in the category. The category is so small, then it's enough. But doesn't always just enough. The category tree at eBay is not very balanced, not very granular. In places like phone or cameras, it's a lot more hard. Luckily, in most of electronics, we have something very similar to Amazon, and that's a catalog. So we can match phones to lenses, cameras to lenses, and match perfectly. It's amazing how it works when you actually have data. We also created clusters based on title similarity. And this is a very good example where in toys, where the recommended category is toys, we were able to match the Ninja Turtle to the entire family of the Ninja Turtles. So I think this is Leonardo on the right side, and then the rest of the family on the left. With properties, the same idea. So once you have a category and this time you have a property, let's say in this case the brand is Nike, then we know the people who buy brand Nike often buy the accessories also brand Nike. If you buy a size small, then it matches a size 30 in pants. That's pretty neat. So once we have that, what else can we do? So we talked about we have different channels. How would they change over time? So we have, as we said, a bunch of emails. So once the user is making a purchase, you see it on the checkout page, but there's also a few emails he gets afterwards. So we thought, how can we improve that? Also in the literature, people started doing a lot of research around that area, and the matrix is no longer a two-dimensional matrix. It's a tensor now when you have the time element. So what we did is we create the same thing. We understood we have 3 time buckets, so we create 3 matrices, or you can think about it as a tensor. Where someone, and this is some of the results we got, which is pretty neat. So the idea is simple, and the results are fantastic. So if someone bought a camera, on the same day of the purchase, we'll get the essentials, like the card, the batteries, and stuff like that. Afterwards, when we send that email of order confirmation, they usually come a day to a week after, then he will get things that he doesn't buy right away, like the strap and the cases. And then a month after, then he probably will be open to lenses, or a week to a month, it will be open to lenses. So it's really nice to see that the data is showing us exactly what we think intuitively would happen if we go to a store and do the same thing. So we implement that. That was nice. And of course, for all those collectors, what we really want to recommend is another camera. So we create a model that detects collectors, so we can recommend them another camera. Awesome. So what do we do? How do we use it? We try to just use Scala, and as for platforms, we use Hadoop, Spark, and Scalding. Now, I don't have a lot of time, so I'm going to rush through this part, although it's pretty neat. So everything I said is real and exists. So you can see, OK, so you're over. But no, really, the tail, the eBay tail, is so vast that we usually, it's not usually, but in a lot of cases when we don't have products, where we don't have categories, or maybe in places like books, there's so many books. So the concept of people who bought this who also bought this is a problem, because there's so many books, and not enough people are buying them on eBay for us to get that statistically significant for us to recommend something that would make sense. So we try to use a content-based recommendation. So I don't know if you know about Word2Vec. I don't have a lot of time to explain, but basically, it's a pre-trained network, deep learning, if you've heard of it, that takes a word and map it to a vector. That vector is dense, and you can simply download it from the Google website. That's what we did. It's commercially open for everyone. Just download and use it, and it's exactly what we did. So every word, like the word R, can be represented by a vector, a dense vector. And that means a lot. You understand why dense vectors are much more different than sparse vectors. There is, in that dictionary that we used, 100 billion words. There's a few other dictionaries, but we used that one. I think is the most popular one. So 100 billion words, and there's 3 million words and sentences there, and every vector is 300 dimensions. So what does Word2Vec do? Once we have this vector, then we can look at closed vectors on the Euclidean space. And that's where it's really started to get interesting, because words like Superman, they match other words like Batman, or Supergirl, my favorite superhero. And that's neat. So if you look at Albert Einstein, you'll get another one of my favorites, Stephen Hawking. That's pretty neat. And if you look at Java, then you get things like coffee. But here comes a really neat part. When you sum vector summation, Java, and code, then you get things that are similar to the Java sensitive code. So we said, OK, let's try that. So we got an email from Tomer, who used to be our director of the group, that he bought this book by Ari Shavit. It's about Israel. He's also from Israel. And in that book, he said, look, I got really bad recommendation. Let's try to fix it. And then someone in my team, Ben, said, check it out. Every book Oh wait, those are the recommendation he got. So at this point, we only have recommend from the books category because we know people who bought books continue to buy books. But yeah, maybe a chocolate and baking book is not the best recommendation for Tomer's Ari Shavit book. So we tried to improve it. And then we noticed that every book item at eBay has a synopsis because we're getting them from the products. That's pretty neat. So if you look at the synopsis, you will see that there was word there that could really help us in content because the word there, so maybe Ari Shavit doesn't say a lot. Maybe the Promised Land doesn't say a lot. But Zionism, Judaism, Palestine, the right to die, that's exactly what we're looking for. So we used word to vec. We said, this is words, let's change them to vectors. So now we're looking for a method that will take a single word representation, change it into collection representation. That's great. So we're looking for a document to a vector. And there has been a lot of research around document to vector, but we tried to do it ourselves because it was still in a preliminary stage. We were literally on par with the research. So now it's about, as I said, taking the document, creating a vector out of it. It's fixed length, so we can then compute nearest neighbors, same way like we did before with cosine similarity. Turns out there was a lot of research about it, and a lot of people are doing it. At the beginning, we said, let's use a simple sum, right? You just, like Java encode, you sum everything together, and then you have a vector, and it's supposed to represent. Doesn't work that good. Sadly, I'm not going to go through how does Fisher vector works, but what we did is we used Fisher vectors. Just Google it online, I'm sure you can find it. It's a really good approach to take all those word-to-vec vectors and change them into one vector that will really represent the document. Once we have that, it became really simple. The Fisher vectors, I have another minute and a half, right? The Fisher vectors converts instead of a 300 vectors, now it's 30 times 300, so it's much bigger. So we have to use LSH, which is locality-sensitive hashing, to find the approximate nearest neighbors, because there's 4 million items in the books categories. And because they're dense and so big, it's not that easy to compute. Even with our huge Hadoop cluster, it's still very hard. So with LSH, we're able to solve it and get good results. Really rush through quickly the results. Now, for Tomer's book, we're not given chocolates. We're given Palestine, the privilege to die, between Jews and Arabs, and things that are actually relevant. Yay. So we launched it to production. We did an A/B test first, and we got a 25% increase on the revenue, and we have a patent on it. And actually, a paper maybe will be published in KDD. We'll see. OK, so it doesn't just work for Tomer's book. It works for other books. Check out the Andre Agassi. Now we're actually given things that are relevant. And we said, OK, if it works for books, maybe it'll work for movies, too. Turns out it does, which is not the right slide. This is the right slide. So Aladdin. So here's the thing. With movies, it's not that big like books. So we end up seeing that even with our collaborative filtering, we get good results. With the content-based, we get also good results. And you will see they're somewhat. So if the collaborative filtering is more about the taste, so some buy Aladdin, also buy Little Mermaid, then the content is more specific, maybe more similar. So if you buy Aladdin, then the Return of Jafar, which is Aladdin 2, I think. So and then we said, OK, let's try to mix books and movies. So if someone buys a book, let's see what movies we can recommend them. Turns out it still works. Although it's different data, we compare the vectors, and they're still similar. So for the book, The Promised Land by Ari Shavit, we got movies like Israel, Birth of Nation, and others. That's pretty neat. It works the other way around, too. So I know you think I came from Israel or care about Israel. It's not true. This is a Vietnam War book, a movie. And here are the books you will see. It's about United States, America, and war in Vietnam, etc. Pretty neat. So I have no more time, so I'm going to talk about the future. Well, it turns out we had the situation of head and tail at eBay, where at the head we have products, very popular products, and for them we have good recommendations using collaborative filtering. For the tail, we really know very little in terms of structured data, although we really tried to tackle that, and the team in Israel is doing a very good and very hard job trying to solve it. It's still hard because when this retailer or when this manufacturer in China create a really unique shirt, it's very hard to describe it. So how do we do that? Well, using the same idea as Word2Vec, we're trying to create a neural network that will solve it. How? Well, you're going to know once we publish. That's it. And we're hiring.